Good morning, all of you. I am Dr. B.B.V. Sailaja, Associate Professor from the Department of Chemistry, Andhra University. Now I am going to discuss on the topic corrosion and its prevention. In this topic, I am going to discuss what is corrosion, why do metals and alloys corrode, what causes corrosion, how much does corrosion really cost, what can be done to prevent corrosion, and finally conclusions. Now let us start with the definitions. And before going to that, let's have some introduction. Man utilized metals and alloys in many ways, from a small pin to a huge machinery. For example, manufacture of household articles, parts for automobiles, ship and aircrafts, construction of buildings and bridges, etc. Now coming to definition, corrosion can be defined as the deterioration of materials like plastic, metals, concrete, wood, etc. by chemical interaction with their environment. The most widely used metal is iron, usually in the form of steel. And corrosion can also be defined as reverse of metallurgy. And another definition for corrosion is effect of environment on materials. Now coming to why do metals corrode? All metals except noble metals like platinum and gold, etc. they are unstable to varying degrees and therefore they exhibit a natural tendency to revert back to their combined state. For example, conversion of iron into its oxide, that is ferric oxide. We call it as rusting. In case of iron, the term rusting will be used instead of corrosion. Similarly, in case of silver, we use it a term tarnishing instead of corrosion. That is conversion of silver into its sulfide and conversion of copper into its green colored carbonate, that is malachite. In case of all other materials other than iron and silver, we call it as corrosion. The most widely used metals, namely iron, aluminium, copper, nickel, silver, and their alloys corrode and lose their appearance and mechanical properties. Most metals corrode on contact with the water and moisture in air. Acids, bases, salts, oils, aggressive metals, polishes, and other liquids, chemicals. Metals will also corrode when exposed to gaseous materials like acid vapors, formaldehyde gas, ammonia gas, and sulfur containing gases, etc. Now coming to atmospheric corrosion. Corrosion by various atmospheres accounts for more failures on a cost and tonnage basis. Atmospheric corrosion is mainly due to moisture and oxygen, but it is accelerated by contaminants such as sulfur compounds and sodium chloride, etc. Now coming to factors affecting corrosion. Water, oxygen, combination of water and oxygen, salt, and flow of electrons out of metal. Now let us discuss these factors by demonstrating with a simple experiments. Now experiment 1, which demonstrates the effect of air and water. In this case, we have to take 3 beakers. In those beakers, we have to drop a nail, and then in the first beaker, we have to leave aside, and in the second beaker, we have to add water and then a layer of oil on the top of the surface of water. And then we have to add, in the third beaker, we have to add water and leave it like that. So after some time, when we observe these 3 beakers, in the first beaker, where there is no water, only air, it is exposed to air, we will not observe any corrosion. In the second case, where the nail is exposed to only water, because the air is restricted by adding oil on the surface of water. So in the second case, we'll observe a little corrosion. And in the third case, where the nail is exposed to both water and air simultaneously, we'll observe more corrosion than the first 2 cases. So the dry nail, in the first case, it will not undergo corrosion, and the nails in water begin to corrode quite quickly, and the nail covered with a layer of oil stops corroding after a few hours, and the nail without the layer of oil continues to corrode until there is quite severe corrosion. Now coming to experiment 2, that is effect of salt. In this case, let us take it as 3 pictures. In the first case, that is experiment A, when aluminum foil is exposed to oxygen and water, it does not corrode, but in the presence of salt, it will corrode. Salt accelerates corrosion by absorbing moisture from the atmosphere. Now coming to experiment B, that is the nail which is attached to red colored cap. When a nail is painted, we are protecting it from both oxygen and water. So there will not be any corrosion. However, when a nail is corroded in a salt and painted, it still corrodes. Salt has a very powerful tendency to absorb moisture even through paints and coatings. Salt speeds up the corrosion of metals, and once a metal has corroded in salt, it is difficult to clean it from the metal surface. Now coming to experiment C. The nail that is corroded in fresh water has been fully protected from further corrosion by paint. But the nail that is corroded in salt water has corroded even though we wipe off all the salt and there was no water under the paint coating. Now coming to another factor, that is combination of metals. Let us discuss the effect of combination of metals with a simple experiment. In this, we will take different combination of metals like copper plus lead, iron plus copper, aluminum plus iron, iron plus copper, iron plus lead, etc. Metals behave differently when they are joined during corrosion. Only one of the pair corrodes, protecting the other metal from corrosion. The nail which is not combined with other metal may corrode a little bit, but when it is attached to other metal, it corrodes more. It all depends upon the electropotential, redox potentials. When copper is attached to solder, copper corrodes more than solder. Now coming to another factor, that is flow of electrons out of metal. This can be demonstrated by taking two nails which are fixed by a battery as shown in the figure, and the tip of the nails, they are dipped in the water. When we observe in the third diagram or a picture, in the third case, I hope you observed the water surrounding the nail, tip of the nail, it became muddy color, reddish brown in color. See, the nail which is attached to the positive end of the battery, the water surrounding the nail which is attached to the positive end of the battery became brownish in color, because here the electrons are flowing out of the metal. Now the corrosion of metal is affected by flow of current. When a current is forced through the metal by a battery, the corrosion can be controlled. So here in this case, the nail attached to the positive end of the battery, the electrons are flowing out of the metal, and the nail attached to the negative end of the battery, the electrons are flowing into the nail. So the metal where the electrons are flowing into it will be protected, and the metal where the electrons are flowing out of it will get corroded. Now the nail attached to the positive end of the battery has corroded significantly, and the surrounding water is muddy brown with rust. The nail attached to the negative end of the battery has not corroded at all. Now coming to occurrence of corrosion. Corrosion, it occurs everywhere. It takes place in all the environments such as air, water, soil, etc. For example, in case of air, corrosion of aluminum fuel tanks in aircrafts, industries, automobiles, bridges, railway tracks, household appliances, etc. Now coming to water, corrosion of ship hulls at riveted joints and equipment used for petroleum exploration, etc. Now coming to soils, underground pipelines laid for supply of water to agricultural fields and underground storage tanks, etc. Conclusion, marine and industrial environments are more corrosive than rural and desert areas. Now, how much does corrosion really cost? So if a single vehicle or car it damages, it costs in lakhs. But when many vehicles, when we take the amount of damage caused to all the vehicles, the damage we cannot, it may be in crores of rupees. So the serious consequences of corrosion has become a problem of worldwide significance. In addition to our everyday encounters with this form of degradation, corrosion causes plant shutdowns and waste of valuable resources, loss or contamination of the product, and reduction in efficiency, and costly maintenance, and expensive over design. So these are all the consequences of corrosion. It can also jeopardize safety and inhibit technological progress. So the cost, it is very huge amount, and not only cost, but safety issues also a matter of concern. Now coming to different types of corrosion, depending upon the appearance of the corroded material. For our convenience sake, corrosion can be divided into different categories. Here it is divided into 8 types, and this is also known as the 8 forms of corrosion. And first one is uniform or general corrosion. Second one is galvanic or two metal corrosion. And third one is crevice corrosion. Fourth one is pitting corrosion. Fifth one is intergranular corrosion. Sixth one, selective leaching. Seventh, erosion corrosion. And the eighth one is stress corrosion. Now, this is another consequence of corrosion. That means when a material undergo damage, it leads to generation of solid waste, and maintenance of this solid waste, it is very difficult and it is very expensive also. And there are many factors which also causes corrosion. For example, dissolved solids and pH, temperature, and concentration of dissolved oxygen, etc. So in conclusion, the consequences of corrosion includes depletion of natural resources. When the more and more material get damaged, we have to replace it by using natural resources. So in that way, natural resources will get depleted, and some damages, they may lead to accidents due to collapse of bridges and damage of automobiles and leakage of pipelines in industries, etc., and generation of solid waste. These are the consequences of corrosion. So now let us see what can be done to prevent corrosion. So corrosion can be prevented by applying coatings and paints, and by using better materials. We have to select materials before going to design that equipment, and better or proper designing of the equipment, and by applying cathodic protection, and by applying anodic protection, and by using inhibitors and chemical additives, we can minimize or reduce corrosion. Now in conclusion, corrosion near marine and industrial environments is more than the rural and desert areas. Corrosion is inevitable. Every material in the universe, it will undergo corrosion, but it can be minimized and its cost can be reduced, but we cannot completely prevent corrosion. Now, let us discuss some basic concepts of corrosion, like polarization, classification, polarization, passivity, corrosion rate expressions, and factors affecting rate of corrosion. Now, we have already discussed about the definitions. Corrosion, it is the deterioration of materials by chemical interaction with their environment, and the term corrosion is sometimes also applied to the degradation of plastics, concrete, wood, and also refers to metals. The most widely used metal is iron, usually in the form of steel, and it can also be defined as destruction of materials by means other than straight mechanical. And another definition of corrosion is extractive metallurgy in reverse. Example, rusting conversion of iron to its oxide, that is ferric oxide, hematite, and tarnishing silver is converted to its sulfide, that is silver sulfide, and conversion of copper into its green colored carbonate, that is malachite. These are some examples of corrosion. And now let us see what are the causes of corrosion? Any spontaneous reaction in the universe, it is associated with lowering of free energy of the system. All metals except noble metals have free energies greater than their compounds. So they tend to become their compounds through the process of corrosion because they are having the natural tendency of converting these metals into their combined state, because in the combined state these metals are very stable compared to their isolated state. So they are having the natural tendency to revert back to their combined state. So the extraction of metals from their ores requires energy. The isolated metals are in a much higher energy than their ores, and they exhibit a natural tendency to revert back to their lower energy state. Except noble metals, all metals are unstable to varying degrees in a terrestrial atmosphere. The most widely used metals, namely iron, aluminium, copper, nickel, silver, and alloys of these metals, all they will get decay and lose their mechanical properties. Factors involved in corrosion, we have already discussed: water, oxygen, and combination of these two, salt, and combination of metals and flow of electrons. Now coming to another classification, that is, we can classify this corrosion into different categories. This is dry corrosion and wet corrosion. It involves direct attack of dry gases, air and oxygen, on the metal through chemical reactions. As a result, an oxide layer is formed over the surface, and this type of corrosion is not common. Now coming to wet corrosion, it involves direct attack of aqueous media, that is strong or dilute, acidic or alkaline, and metal through electrochemical reactions. The moisture and oxygen are also responsible. This type of corrosion is quite common. So dry corrosion takes place under dry conditions, and wet corrosion under wet conditions like acidic environment or alkaline environment. So now coming to dry corrosion, this type of corrosion occurs by direct chemical attack of atmospheric gases like oxygen, halogens, hydrogen sulfide, etc. on the metal surface. It is again categorized into corrosion by oxygen or oxidation corrosion and corrosion by other gases. Now coming to oxidation corrosion, that is corrosion by oxygen. So it is due to chemical attack of oxygen on the metal, resulting in the formation of metal oxide layer. This metal oxide layer formed by combining this, interaction of this oxygen on the metal surface. First, this metal will undergo oxidation, and this oxygen will undergo reduction, and they both combine to form metal oxide. This theory is called Wagner's theory. Now, nature of metal oxide layer. So the metal oxide layer, in some cases, it may be thick, it may be thin, or it may be stable, or it may be unstable. So depending upon the nature of the oxide layer, again, we are categorized into stable oxide layer. That means it acts as a barrier between the metal and oxygen. So this stable oxide layer, it prevents further corrosion. Unstable oxide layer, it will not prevent further corrosion because it decomposes back to metal and oxygen. So silver, gold, platinum are protected by this manner. These metals, they form silver, gold, platinum, they form stable metal oxides. That's how they will get protected. Now coming to high temperature and low temperature corrosions. Now this is another classification, and high temperature corrosion means it is a form of corrosion that does not require the presence of liquid electrolyte. Sometimes this type of damage we call it as dry corrosion or scaling. So high temperature metals requires neither moisture nor dissolved electrolytes. Now low temperature corrosion. It appears in the boiler as well as on the other surfaces where the temperature is under approximately 135 degrees centigrade. It is caused by condensation of the acidic sulfur and chlorine containing gases. This type of corrosion is temperature dependent, and new plants are being designed differently in order to avoid low temperature corrosion. Now wet or electrochemical corrosion. So this type of corrosion takes place only under certain conditions. Now let us see what are the conditions which leads to wet corrosion. When there is a liquid in contact with a metal to conduct, in this case, wet corrosion takes place. And another condition which leads to wet or electrochemical corrosion is when there exists a difference of potentials either between two dissimilar metals or between different areas on the surface of the metal. So in these two cases, that means when there is a liquid in contact with metal for conducting, and when there exists a difference of potential either between two dissimilar metals or between different areas on the same surface of the metal. Under these two conditions, wet or electrochemical corrosion takes place. In order to understand this wet or electrochemical corrosion, we need to have some basic knowledge of electrochemistry. So now let us see the basic terms we come across in corrosion. They are anode, cathode, electrolyte, and metallic path. So these are the basic terms which we come across. Now anode means it is an electrode through which electric current flows into a polarized electrical device. And the misconception is that anode polarity is always positive. This is often incorrectly inferred from the fact that in all electrochemical device, negatively charged anions move towards anode, or oppositely charged cations move away from it. Anode polarity depends on the device type and sometimes even in which mode it operates. Cathode, it is one of the two electrodes. That means another electrode in an electrolytic cell represented as positive terminal of the cell, and a reduction takes place at cathode and electrons are consumed. So oxidation takes place at anode and electrons will be released at anode and the metal will get oxidized. And now coming to electrolyte, it is the conducting medium or conducting solution that must be present for corrosion to occur. So pure water is a bad conductor of electricity. So in pure water, corrosion will not take place. But electricity passes from anode to cathode through electrolyte as cations. For example, zinc 2 plus ions dissolve from a zinc anode and thus carry positive current away from it through the aqueous electrolyte. Now metallic path. The two electrodes are connected externally by a metallic conductor. In the metallic conductor, conventional current flows from positive end of the cell to negative end, which is really electrons flowing from negative to positive. Metals provide a path for the flow of conventional current, which is actually passage of electrons in the opposite direction. Now current flow. Conventional current flows from anode to cathode as zinc ions pass through the solution. The current is carried by these positively charged ions. The circuit is completed by passage of electrons from anode to cathode through the external metallic wire circuit. Now mechanism of corrosion. The mechanism of rusting is found to be electrochemical in nature. Anode and cathode are involved. Electrons flow from anode to cathode. Oxidation of iron to iron 2 occurs at anode and several reduction reactions takes place at cathode. At anode always only oxidation will take place, but at cathode different reactions takes place depending upon the nature of the material. At anode areas of iron, the iron is electrochemically oxidized to iron 2. In an oxygen environment, the iron 2 is quickly oxidized to iron 3, which is subsequently changed to ferric hydroxide and finally to hydrated ferric oxide. Now coming to electrochemical principles. So we need to understand these concepts like standard electrode potentials, EMF series, galvanic series, galvanic or electric or voltaic or Daniell cells, and concentration cells and reversible cells. These are the electrochemical principles based on which the corrosion will takes place. So in order to control corrosion, we need to understand these basic concepts. If we are able to understand these concepts, we can apply these principles and somehow we can minimize or control corrosion. So this is about electrochemical series and the standard, the standard redox potentials of all the metals are measured with respect to hydrogen. Hydrogen is taken as the standard one, and with respect to hydrogen, the standard redox potentials of all the metals are measured, and it is the standard redox potentials of these metals are arranged in a series. And from hydrogen, see, hydrogen is at the center with zero potential, zero electrode potential, and on the top of the hydrogen, when you observe, on the top of the hydrogen, we are having positive electrode potentials, and the bottom of the hydrogen, the metals which are having negative electrode potentials in an increasing order. Now, see, when you observe increasingly active anodic on the lower side and increasingly inert or cathodic potentials on the upper side of hydrogen. Now, we can study corrosion and standard corrosion. For example, when we take iron and copper, see here iron, where is iron? When we connect iron and copper, iron with a potential of plus 0.771 and copper with a potential of plus 0.340. So iron is having more positive potential than copper. So the one which is having more positive potential will act as cathode, and the one which is having less positive or more negative will act as anode. So when we combine iron and copper, obviously copper will act as cathode and iron will act as anode. So here iron will go into the solution and copper will get deposited. Iron will go into the solution in the form of iron 2 plus ions and copper will get deposited. It will get reduced at cathode when we combine copper at cathode, and when we take iron as anode, iron will get oxidized. That means it will get corroded and it will get dissolved and it will go into the solution as iron 2 plus ions. But here at cathode, copper ions will undergo reduction and the copper will be deposited on the copper cathode. So the overall cell reaction is 0.780. Now coming to iron versus zinc. Here zinc is having more, in the series, when we observe zinc is having negative redox potential. So zinc acts as an anode and iron acts as a cathode. So zinc will get dissolved into zinc 2 plus ions and will go into the solution. So zinc will undergo corrosion when we combine with iron. Iron will get protected. Iron will undergo reduction. Iron 2 plus ions will undergo reduction and iron 2 will deposited. Iron will get deposited on cathode and zinc will dissolve. It will undergo oxidation and the zinc 2 plus ions will go into the solution. Similarly, when we combine iron and copper, iron acts as an anode, copper will act as a cathode. So iron will get corroded and the copper will get protected. So that's how, with the help of electrochemical series, we can assess, we can predict which metal will act as anode and which metal will act as cathode. So this knowledge of electrochemical series will help us to protect, to control corrosion. So mechanism. Suppose when we take zinc, at anode, what is happening? Oxidation of zinc will take place. Here at anode, zinc will oxidize to zinc 2 plus ions. Zinc 2 plus will go into the solution and the electrons will flow towards the metal and they will get accumulated on the surface of the metal. So at the surface of the metal, what happens? The H plus ions present in the medium, conducting medium, that is acid solution, they will take these electrons and they will get reduced and they form hydrogen gas at cathode. So at anode, zinc will get oxidized to zinc 2 plus ions. This part will act as anode and this part will act as cathode. So at cathode, hydrogen gas will be liberated. So mechanism of wet corrosion. At anode, always oxidation will take place. At cathode, different reactions will take place. If you take acid solution, then hydrogen evolution takes place. Sometimes oxygen reduction also takes place. So it will enhance cathodic reaction. Whenever cathodic reaction is enhanced, automatically anodic reaction is also enhanced and corrosion, rate of corrosion is more increases. So, and at cathode, oxygen reduction will take place in acid solution or neutral or basic solution, and metal ion reduction and metal deposition. These are the different reactions takes place at cathode depending upon the nature of the cathode or material or medium. But at anode, irrespective of the environment, oxidation takes place. Now coming to prevention of wet corrosion. In case of impure hydrochloric acid, suppose if we take impure hydrochloric acid medium, where iron 3 plus ions will be present in the hydrochloric acid as impurity, these iron 3 plus ions also will enhance the rate of corrosion. So if we remove the impurity, that is iron 3 plus ion, from the hydrochloric acid, then we can minimize the rate of corrosion. And oxygen reduction, we can prevent this cathodic reaction, that is oxygen reduction, by preventing air. So further reduction will be stopped. And coating with paints. By coating the anodic and anodic part with the paints, we can suppress the anodic and cathodic reaction. By suppressing anodic and cathodic reactions, we can minimize or prevent further corrosion. And by adding inhibitors means high molecular weight amines. By adding these inhibitors also, we can minimize anodic and cathodic reactions. And finally, we can minimize corrosion. And decreasing conductivity of the electrolyte. When we decrease the conductivity of the electron, the flow of electrons will be stopped. So that's how we can minimize or we can reduce corrosion. Now coming to another concept, that is polarization. There are different types of polarization: concentration polarization, anodic polarization, cathodic polarization. So the concentration gradients at the electrodes, they set up a back EMF and the potential drops. And anodic polarization. Example, we can minimize this anodic polarization by adding depolarizing agents. Similarly, cathodic polarization, we can minimize or reduce cathodic polarization by adding depolarizing agent, for example, manganese dioxide. Now coming to passivity, this is another concept we observe in corrosion. So passivity means it is loss of electrochemical reactivity, thereby decreasing the rate of corrosion of the metal. So there are some materials, they exhibit this nature, that is passivity. That means they act as if they were like a noble metals. So there are some materials under certain conditions, they behave like a noble metals, and they will not undergo corrosion. That's how we can protect the materials. So for example, when we observe the curves of this passivity, it will be like this. Now coming to passivity means it is loss of chemical reactivity of a certain metals and alloys under particular environmental condition. Let us see what are the conditions under some metals, they behave like a passive metals. For example, certain metals and alloys, they become inert and act as if they are noble metals, such as platinum and gold. The metal which exhibit passivity effects are iron, nickel, silicon, chromium, titanium, and alloys of these metals. Only these metals, they exhibit passivity. That means they become passive under certain conditions. Let us see what are the conditions they will become passive. Under limited conditions, zinc, cadmium, tin, uranium, and thorium also show passivity effect. So behavior of passivators. Same metal can act as active as well as passive depending upon the situation. Same metal under a certain up to certain level, it will act as passive. After that, it will act as active. After again, it will become passive. So it all depends on the nature of the environment. If a metal is immersed in an air-free acid solution, it will undergo corrosion. But increasing the oxidizing power of the solution, that means by adding oxygen or ferric ions, it increases the rate of corrosion. So this is the active state of the metal. So it will continuously undergo corrosion. As shown in the figure, see, it is like a straight line. So the rate of corrosion increases with concentration of the oxidizing material or oxidizing power. That is normal metal. Now coming to passive metals. Now that means the metals which exhibit passivity. In this case, what happens when we add more oxidizing agent, it will undergo corrosion to a certain extent. When if we further increase the concentration of the oxidizing agent, it will stop corroding. It will remain stable for some time. And again, if we further increase the concentration of the oxidizing agent, then it will again undergo corrosion. So we'll observe three regions. Region 1, we call it as active region. Region 2, that is passive region. And region 3, that is trans-passive region. This is the passive state of the metal. See, for the metals which exhibit passivity will show this type of curve. So in this case, in the first region, that is active region. In the active region, the rate of corrosion continuously it is increasing with the concentration of the oxidizer. After some time, it is becoming stable. Why? Because here at a particular concentration, it forms a protective layer. The material, the material which exhibit passivity, they form protective layers. And if we further increase the concentration of the oxidizing power, that protective layer will get dissolved and the metal will be exposed, and again it will undergo corrosion. That is transpassive region. So it will show the metals which exhibit passivity, they show these three regions: active, passive, and transpassive. Now coming to corrosion rate expressions. So in order to compare the materials under different conditions, we need to have some units. So it can be expressed, corrosion rate can be expressed in terms of weight loss in grams or milligrams. But it will not, these units will not include any time of exposure, because corrosion also depends upon time of exposure. If you expose for a few minutes, the corrosion is less. If you expose for hours or days or years, the corrosion is more. So we cannot compare. So we have to take into consideration, along with weight loss, we have to take time of exposure also. So that is modified, the units, first one, that is modified to second, that is milligrams per square decimeter per day, MDT, or grams per square decimeter per day, GDM. Or we can also express it as grams per square meter per hour, or grams per square inches per hour, grams per square centimeter per hour. So this second category of expressions, they include time of exposure also. But in some cases, we have to take into consideration the penetration power also, because some cases the corrosion will penetrate deeply into the metal. So we have to take into consideration. So by modifying the expressions 1 and 2, we'll get third one, that is inches per year. We can express the corrosion rate in terms of inches per year or inches per month. And by taking into consideration all the factors like weight loss and time of exposure and penetration, everything, finally, by including all these factors, a new way of expressions was proposed internationally and accepted by many, and accepted internationally, that is mils per year, MPY. So mils per year, that is expressed by a formula, that is 534 W by DAT. W means weight loss in milligrams, A is the area of a specimen, that is inches square, and D is density of the specimen, and T is exposure time. By including all this, we can express corrosion rate in terms of mils per year. Now coming to factors affecting the rate of corrosion, we have already discussed the other, some physical factors they affect, like effect of oxygen, effect of water, and combination of oxygen and water, etc. Now these are also some factors which affect rate of corrosion. Previously we discussed about factors affecting corrosion, and these are the factors which affect rate of corrosion. By controlling these factors, we can reduce or minimize the rate of corrosion. So first one is effect of oxygen or oxidizers, and effect of velocity, effect of temperature, effect of corrosive concentration, and effect of galvanic coupling. Now coming to effect of oxygen and oxidizers. So an increase in corrosion rate followed by a rapid decrease, and then a corrosion rate which is independent of oxidizer concentration. It is characteristic of active passive metals, just like we have discussed passivity. So the metals which exhibit that passivity, they will show this type of curves. So it shows the effect of oxygen on oxidizers on the rate of corrosion. So when we increase oxygen or oxidizing agent, the concentration of the oxidizing agents, the rate of corrosion in case of passive metals first increases, and again it will decrease, and again it will increase. I have already discussed in the first case, the corrosion initiates and it will progresses, and after some time it will form a protective layer and the corrosion will remain. It will be stopped, and the metal will be stabilized, and again the protective layer will be removed after a certain concentration. Again the metal will be exposed and the rate of corrosion increases. as shown in the picture, region 1, 2, 3. Region 1 is active region, 2 is passive region, and region 3 is transpassive region, as we have discussed in passivity. Now coming to see examples. In case of Monel, that is 70% nickel and 30% copper. It is an alloy in hydrochloric acid plus oxygen. That shows region 1. That means the corrosion increases continuously. And another example is copper in sulfuric acid plus oxygen, which is exposed to oxygen. So these two exhibits the region 1, the curve shown in the region 1. And coming to 1 and 2, that means up to a certain level, the rate of corrosion increases, and again it will stop and it will remain stable. That is region 1 and 2. This type of curve we will see in materials like 18 chromium, 18 nickel in sulfuric acid plus iron 3 impurity, and titanium in hydrochloric acid plus copper 2 plus. And now coming to region 2, that means only passive region. It will not undergo corrosion under any environment. It will remain constant. Example, 18 chromium, 18 nickel in nitric acid and haste alloy C in ferric chloride. In these two materials, it shows passivity. And now coming to 2 and 3, that means initially it is stable, and after some time the rate of corrosion increases. After up to a certain concentration level, the material will not undergo corrosion, and beyond that the rate of corrosion increases. Example, 18 chromium, 18 nickel in nitric acid and chromium oxide. And there are materials like 18 chromium, 18 nickel in sulfuric acid plus nitric acid. In this case, these material will exhibit all the three regions. That means active, passive, and transpassive regions with concentration. When we increase the concentration, initially they will be very active, and then they will become passive, and then again they become active. Now coming to effect of velocity. That means velocity of the corroding medium or oxidizing medium. In the curve A, see, initially it will increase, and again it will decreases and remain stable. Examples of materials which exhibit this type of behavior, that is curve A, are iron in water and oxygen, copper in water and oxygen, 18 chromium, 18 nickel in sulfuric acid and iron 3 plus, and titanium in hydrochloric acid plus copper 2 plus. And now coming to curve B, that is the corrosion rate remains stable with velocity. Even if you increase the velocity of the medium, the corrosion, they will not undergo, the material will not undergo any corrosion. Example, iron in dilute hydrochloric acid and 18 chromium, 8 nickel in sulfuric acid. Now coming to curve C, the materials like lead in dilute sulfuric acid, iron in concentrated sulfuric acid exhibit the behavior of C. Initially, the rate of corrosion slowly increases and drastically increases. After a certain level, it drastically increases. This type of behavior is shown by lead in sulfuric acid and iron in concentrated sulfuric acid. Now coming to effect of temperature, we'll observe two types of behavior, that means curve A and curve B. Materials which exhibit the behavior of curve A, that means it gradually increases. Initially, it will slowly increase and then gradually increases. Curve A, example, 18 chromium, 8 nickel in sulfuric acid, nickel in hydrochloric acid, iron in HF. Now coming to behavior curve B. Initially they remain stable up to a certain temperature. When we further increasing the temperature, then the rate of corrosion increases. Example, 18 chromium, 8 nickel in nitric acid, monel in hydrofluoric acid, and nickel in sodium hydroxide. Now coming to effect of corrosive concentration. We'll observe two types of behaviors, curve A and curve B. In curve A, we'll observe a peak, it will increase and again it will decrease and slowly it will decrease. In case of curve B, it remains stable up to a certain corrosive concentration and then it rises. So for curve A, the examples include nickel in sodium hydroxide, 18 chromium, 8 nickel in nitric acid, acetyl B in hydrochloric acid, tantalum in hydrochloric acid. Now coming to in curve A, region 1 and 2, monel in hydrochloric acid, lead in sulfuric acid. Now coming to curve B, initially it is stable up to a certain level and then further rises. Aluminum in acetic acid and nitric acid, 18 chromium, 8 nickel in sulfuric acid and iron in sulfuric acid. With this I conclude. Thank you.